Um, so thank you all for your presence. Thank you, Philip, for accepting this invitation. So Philipp Höhn is an associate professor at Okinawa. So I'm taking your curriculum here from your page, Philip. So he did his PhD in Utrecht in the Netherlands. He was a postdoctoral research at Perimeter and also at ECOC in Vienna. He was a research fellow at London and also an honorary associate professor. And right now he is at Okinawa. I think if there is something you would like to add about your curriculum, feel free. And please go ahead with the seminar. And those who would like to interrupt him, you can just raise your hands or unmute yourself for making questions. So thank you very much.
Yeah, thanks very much, Natalia, also for the invitation. So this talk will be about entanglement entropies in perturbative quantum gravity, and in particular how the description of these changes when you introduce what Witten and so on have recently called observers. So this will be quite a lot about algebras, regional algebras in perturbative quantum gravity. And so Natalia had asked me to talk about something that involves clocks. And so you might at first wonder what this has got to do with clocks, but it turns out that, as I will explain, what these observers are really, I mean, they're modeled by quantum clocks, and really this is about temporal quantum reference frames and relational dynamics, this thing. And kind of the crux is that when you describe the regional quantum field degrees of freedom relative to these quantum reference frames, that it leads to what you could call an intrinsic regularization of the entanglement entropies. Okay, so this work that I'm going to present is based on the sequence of papers that we wrote last year. And in particular, if you want to have a somewhat slightly less formal summary of it, then there's this paper here, the first one from about a year ago. Okay. Yeah, so we start with basics of entanglement entropy. So as most of you will know, entanglement entropy in quantum field theory is intrinsically UV divergent, and that's because there's infinitely many degrees of freedom around the entangling surface. And mathematically, a somewhat more precise way of phrasing this is that the algebras that are associated with regions, such as, for example, a static patch in a de Sitter space, that they're so-called type 3 von Neumann factors. And that means that these algebras don't possess any traces. When you don't have traces, then you can't define the usual von Neumann entropy. In particular, you can also not define any density operators. And then what one typically does is, at least in standard treatments, is that one introduces regulators into the game, some kind of UV regulators, and that effectively acts like converting these algebras to type 1 algebras, in which case you have something like traces and so on, and then you can compute density operators, but this is something that, in a covariant theory is not very attractive, particularly not in gravity, because these regulators are in tension with covariance, and the issue is that removing them somehow restores these divergencies. Now, when we're interested in entanglement entropy in gravity, the situation changes slightly. So typically, at least in semi-classical and perturbative quantum gravity, one is interested in what is called the generalized entropy, so associated with a region, which is basically an area term, and then the usual Q of T entropy associated with that region, which would be basically the one that's from the previous slide, the UV divergent piece. And this is, for example, something that you can get from a Euclidean path integral description. And the general expectation is that, in fact, this generalized entropy, that this should be something that is finite based on renormalizing the Newton constant, the bare Newton constant. And for instance, one can think of this divergent piece here as, or at least that's the hope, as a renormalization of this bare Newton piece here. And one other reason why this entropy is interesting, this generalized entropy, is that it's expected to obey the generalized second law for at least regions that are bounded by horizons. Goes back to Bekenstein, and versions of it have been proven by Wall, and some further versions have been proven recently. But in any case, the fact that it's supposed to be finite suggests that there should hopefully be, for generalized entropy, a somewhat more rigorous mathematical definition without any kind of regulators in gravity. And this is something that will be connected also more generally with the question of actually how to define a subregion in a gravitational context, because we have diffeomorphisms. In particular, when we include now gravitons, the situation changes compared to a Q of t in some fixed background in the sense that we actually have to impose now gauge constraints, so diffeomorphism constraints. And recently, there's been a very interesting development by Chandrasekaran, Longwood, Pennington, and Witten that I will probably mostly call CLPW in what follows, where they have considered perturbative gravity in the G Newton going to zero limit. And basically what they've done is, so the main case that they look at, so they also look at black holes, but the main case they look at is actually de Sitter space. So here's a conformal diagram of de Sitter space, and here I'm just drawing two patches, U prime, two static patches. So if you're not so familiar with these diagrams, every point in this diagram is actually in S2, except on what looks like a boundary. There's, of course, being de Sitter space, it doesn't actually have a spatial boundary. But what looks like the boundary here, they're just basically North Pole or South Pole trajectories of an observer. And so they considered de Sitter space and Q of t inside it, including gravitons. And what they showed is that if you introduce two antipodal static observers, here labeled by gamma and gamma prime, that they're in fact modeled by clocks when you introduce them into this game. And then you impose a killing boost constraint. So this is one of the diffeomorphism constraints in perturbatively de Sitter space that is associated with this cosmological horizon. They then show that the algebra of quantum field observables that you associate with either of these patches, and in particular it includes gravitons. When you take those observables, these algebras, and you dress them to these observers, we'll come to what is meant by that later, that these dressed algebras are what are known as type 2 von Neumann algebras. And this is significant because type 2 algebras, they actually have a well-defined trace, and so they have density operators that you can derive from that. And that means in particular that you can also derive a notion of von Neumann entropy from it. And you can think of that as a renormalized entropy. So it seems, and then one other thing is that what they also showed is that at least for certain semi-classical states that you recover this generalized entropy that I talked about on the previous slide. And so you could think of this as a somewhat more rigorous way of obtaining these results. And so you see that actually taking into account diffeomorphism invariance, at least perturbatively, and okay, here introducing a notion of observer somehow provides for what you could think of as an intrinsic regularization. And it might suggest a path for a somewhat more rigorous definition of entanglement entropy in dynamical gravity. Okay, and so this has been generalized to black holes, some general subregions, and in fact, this has been a pretty popular subject recently, and there's a whole new industry, so really zillions of papers on this. But yeah, basically the work that I'm going to present sits in this new industry. So now what is this talk going to be about? So I want to explain a bit better how one should think of these observers that they talk about, and then the so-called cross products. These cross products are these dressed observable algebras. And as I will explain, these observers are nothing really but quantum reference frames. And these cross products are essentially relational observable algebras, particular quantum reference frames. They're temporal quantum reference frames, quantum clocks, and these relational observables basically describe the evolution of quantum field degrees of freedom relative to these clocks. Then I will discuss why it is legitimate to consider just a single constraint, or in which sense it is legitimate. So as I mentioned on the previous slide, CLPW only considered a single boost constraint, but gravity is a field theory. There's infinitely many constraints. So why would that be sufficient for what they want to do? And it turns out that this has something to do with these constraints being what are known as linearization stability conditions, and there's only finitely many of those. And the one that they look at is just one of them. The others won't affect the argument. And then the final question is, what can we actually do with this observation? That we can think of these observers as quantum reference frames. And one of the things that we can look at is to generalize this to arbitrarily many observers, and then look at frame covariance, and in particular look at how this gravitational entropy or the regional entropy will depend on the observer. And so altogether, what arises from this is that basically these dress descriptions by Witten and so on, you can really think of them as being relational descriptions of the regional QFT degrees of freedom, and in particular the entropies relative to these quantum reference frames. And somehow this introduction of quantum reference frames intrinsically regularizes these entanglement entropies. Now in the title, I had this wording of gravitational algebras. So this is something that in this community has arisen now. Really what is meant by this is that we're talking about algebras of regional diff-invariant observables in this perturbative quantum gravity setup. So that's what is meant by that. Okay, so here's the menu of the talk. So I'm not sure that everybody's familiar with basic notions of von Neumann algebras in quantum field theory and modular theory. So I will give a few, like a really lightning review of some of the basics of this that are relevant for the subject. Then we'll talk very briefly about quantum reference frames, also basically a nutshell review, and then I will explain the slogan PW equals CLPW, which essentially means that PW stands for Page-Wootters, which is to say that the formalism used by CLPW is equivalent to the Page-Wootters formalism, and also to highlight that these observers are quantum reference frames. And then hopefully if I have some more time, I will explain why these regional gravitational entropies are, or in which sense they're observer dependent. Okay, so here's a very brief overview over von Neumann algebras and in quantum field theory. So what is a von Neumann algebra? So here's just a very basic definition. I had a bit more on this, but I guess there's not that much time in this talk. So really, more generally in quantum theory, we're typically interested in bounded operators on a Hilbert space. So that's what this here is. And bounded operators are nice because you can multiply them as you will, and it will give you another bounded operator. So they form nice algebras. And in any case, usually observables that we are interested in, there should be bounded operators because we don't usually measure anything that's infinite. And so in particular, we're interested in subalgebras of bounded operators. And typically, we're also interested in what are star algebras. So star algebras means they're closed also under the adjoint, so under Hermitian conjugation. And of course, it should also have a unit inside, so an identity element corresponding to nothing happening. And now we are going to be interested in a particular set of such subalgebras of bounded operators that are closed in a very precise sense. There exist equivalent ways of defining this. But von Neumann algebras are basically defined by the property that they're closed under bicommutation. And what that means is that so first of all, if you look at the commutant of an algebra A, so that's just the set of the set of elements in the total algebra, so the total algebra of bounded operators on the Hilbert space that commutes with that algebra. And if you take the commutant of the algebra you're interested in, and then you take the commutant of the commutant, then you get back the original algebra. That's what this here says. That is the property of von Neumann algebras. So that defines your closure under commutation relations. And these objects are quite interesting in quantum field theory. So in quantum field theory, typically one takes that the algebras of what are, you can think of observables that are localized to a region, such as, for instance, here again, a static patch in the de Sitter space. So you associate that, with the causally complete region. That's somewhat important. It's usually taken to be a von Neumann algebra. And when we talk about local observables, what we mean by that is really you basically take the algebra or the von Neumann algebra generated by local field operators smeared with smearing functions that have support in this U, and then basically you look at the von Neumann algebra that's generated by those. Now, it has some nice relations also with the causal structure. So if we have two causal complements, such as two antipodal static patches, then, well, space-like separated observables, they should commute. So we want to have this. And what that really tells you is that basically the algebra of the causal complement is contained in the commutant of the algebra that we might be interested in. And typically in quantum field theory, you assume, or it's sometimes also taken as a postulate, what is known as Haack duality, where you make it even stronger, where you actually basically equate the commutant with the algebra of the causal complement. So when you have this, then these regional algebras, these regional phenomena algebras that are associated with a causally complete region are also causally complete in this sense. So this has a very nice feature. So it's not always true, Haack duality, but at least in, I think, most interesting cases it is. Now, when we want to talk about entropies, then we want to think of subsystems. And typically in quantum mechanics, we think of tensor product factorizations of Hilbert spaces, and then we want to somehow trace out one factor. So when you have regions U and U prime in quantum field theory, then you cannot just do this. The global Hilbert space doesn't factorize across this entangling surface in this way. But what you can do is you can define an algebraic notion of such a factorization, basically. So suppose when you have a tensor factorization of this, then it is also true that the algebra is supported on one side and the other side, that their intersection is just basically multiples of the identity. But the converse is not necessarily true. You can also have, of course, observable algebras whose intersection is just the identity. And when you do this for the regional algebra as commutant, then these regional algebras are known as factors. And so you can think of this as a kind of generalization of subsystem factorization. And so this is interesting for computing entropies later. Okay, so modular theory turns out to be pretty important in the subject. If you're not so familiar with it, okay, it takes a bit to get used to it. I'm just going to give you a very basic ingredients. This is also known as Tomita-Takasaki theory. And basically, the main thing that we're going to be interested in is the modular operator. And essentially, whenever you have a state psi that is in some sense sufficiently entangled, so the precise way of saying that is that the state is what is known as cyclic and separating, as I put here in this asterisk down there in this footnote. And indeed, when you think about it, cyclic and separating is something that, when you think about it, for instance, finite dimensional algebras, it tells you that for when you have two finite dimensional Hilbert spaces and you look at the sort of algebra supported on one and the other, then cyclic separating states are those that are actually maximally entangled across that factorization. And so, but you can define cyclic and separating also when you don't have such a factorization in these algebras. And so, but you can think of this in some sense as a sort of more formal generalization of saying sufficiently entangled. That's why I put this in quotation marks there. But whenever you have such a state, then you can define what is called a modular operator. I won't give you the precise definition here. What is important is that it's a positive operator and that it defines automorphisms of these regional algebras. That means if you define a flow, so T is just some real parameter, and so you basically, you basically exponentiate this modular operator, and then the flow that it generates leaves this algebra invariant. And so because it is a positive operator, what I can now do is I can define the log of this modular operator, and this is known or this is what is known as the modular Hamiltonian. And I can think of this here basically as defining a modular time evolution. So at this point, this is pretty abstract. We're just talking about some, states, some algebras. But the interesting question is when this modular flow can be related to something that is actually geometric or a diffeomorphism, or when it actually corresponds to physical time evolution in space-time. And in general, the answer to this question is not actually known. But what is known is that when you have killing horizons, such as in the Zitter space, when you have a static patches, so this here is the cosmological horizon, the bifurcation surface there. When you have such killing horizons, then the boost Hamiltonian that is associated with this killing horizon is actually modular for the vacuum state or some K-mass state. And okay, there exist various studies of this. So intuitively, you can think of this that these boost Hamiltonians, the boost killing fields, the flows, they leave these regional these causally complete regions invariant. So they should also, when you look at the Hamiltonians corresponding to this, they should leave the regional algebras invariant. So they should generate automorphisms for this. So in that sense, it's not surprising that they generate automorphisms for this, but the non-trivial thing is that they actually correspond to the modular Hamiltonian of some vacuum state. Okay, now we will be interested in these modular Hamiltonians that will be important later in this discussion, and we will in particular want to impose them as diffeomorphism constraints in this context when they are boost Hamiltonians, and boost Hamiltonians corresponding to certain diffeomorphisms in the closed universe, so they are gauged. Now, one important question in this context is whether or not this modular operator is actually contained in a regional algebra, or whether you could split it into pieces that are contained in it. So when I look at, for instance, these the modular Hamiltonian, is it possible to split it into a piece that has support in one regional algebra and in its commutant? And it turns out that is not feasible in quantum field theories because these splits turn out to be UV divergent, so this doesn't actually exist. And that's just another way of saying that the flow that is generated by these modular Hamiltonians is what is called an outer modular flow, which means that the generator of this flow is not actually contained in these algebras. And that's a defining feature also of these so-called type 3 algebras. Now, when we want to discuss entanglement entropies, we need to have a notion of trace in order to define what is a von Neumann entropy. And let me just give you a bit of an intuition of how one can think of a trace in these von Neumann algebras, because it works a little bit differently than in the usual context of finite dimensional Hilbert spaces, say, in particular these traces in these rather complicated von Neumann algebras, they are not Hilbert space traces. And so I'm just going to do a bit of an intuition here. So suppose we have this.
Before we continue, I think we have a question. Albert, feel free.
Yeah.
Yes, I mean, it's really maybe a little bit of a tangential question. By the way, very interesting talk, very nice on this topic, explaining very clearly. So my question is a little bit not really following. I understand that the main thread of your what you're saying, I understand that we will consider these entanglement entropies and so on. So these entangled states are important, but I was just wondering, when you mentioned here, given sufficient entangled state, you have this property here. If one was not interested in entanglement entropy in this particular setup, how important is that sufficiently entangled to define this property on just something that was defined here for one particular region?
Are you asking how important is it to define something like a modular operator, or?
So I guess the statement here, as I said, I understand that this is a bit of a side question, but the statement here is given any sufficient entangled state, we can define a positive operator that has that property on one particular region, U, as you define it there. So
so it turns out that this is basically also the modular operator for the complement region. So the two modular operators, they're related to one another. So, but you can do this for any, you can do this for any region basically in space-time, any causally complete region, as long as you have a cyclic separating vector of the global Hilbert space. So what the important thing is, of course, this psi here lives in the global Hilbert space of the total space-time, the QFT in the total space-time. It's not a state associated with the region, I should say. Okay, but
yes.
Yeah, does that help? Yeah. So, but you could, in principle, look at modular operators for a given global state for any for any region, as long as that state happens to be cyclic separating for the regional algebra. Okay.
Okay, I think.
So okay, I mean, the definition of cyclic separating is down here. I didn't want to go into details of it. It's a little bit technical, but yeah, the statement is whenever you have an algebra associated with whatever region U, doesn't matter which one. I mean, so okay, it's causally complete. It should be, and then and you have a global state that's cyclic separating with respect to that algebra. Then you can define a modular operator for this algebra, and it automatically defines also one for its commutant.
Okay. Thank you.
But it's crucial that it is cyclic separating. If you don't have that feature, in particular, if you don't have separating, then you can't define that operator.
Okay, thanks.
Okay. Yeah. So maybe coming to the notion of traces in these phenomenon algebras and these more complicated phenomenon algebras. So I'm just a bit of intuition. So suppose we have now this modular operator, and you could factorize it into a piece. I'm just going to call it rho psi and rho psi prime inverse. And rho prime are affiliated with well, the algebra A and A prime. So the algebra and its commutant. Suppose that was possible. So as I just explained on the previous slide, this is impossible for type 3 because so if I could factorize this modular operator in that way, that would entail that I could split this modular Hamiltonian in this way, which I just said is impossible in that case. So what I'm doing here on this slide here is impossible for type 3 algebra, so the standard QFT algebras. So this is related to the fact that these algebras don't have traces. Now, let me give you a bit of an intuition of how you can define a trace now for regional algebra if this is satisfied. And this is basically what is going to be used later. So basically, when we want to define a trace, one of the basic properties that we want to have, of course, is that a trace defines basically a cyclic functional on the algebra. So if we have some elements A and B that reside in that algebra, we just want to have that it's equal to the trace of BA. And you can define you can define a trace by such a sufficiently entangled state, and you invert and you put here basically the inverse of this guy inside here. So the fact that you can invert these objects is already suggesting that this must be sufficiently entangled. And indeed, if you wanted to do this with finite dimensional algebras, then you need to have that these row states are actually full rank states, which is guaranteed by the cyclic separating feature that I mentioned. So this is basically the reason also why you need that they're sufficiently entangled. Now there's another property from this modular operator that satisfies this part of its defining identities. You can basically flip the ordering of these elements that lie in the algebra in this expectation value. And when I do this, I can rewrite this in this manner here. So what I'm showing now is just cyclicity, basically. Then I can make use of the fact that this guy here I'm using this assumption now, which basically kills this row inverse here with that guy, and then I replace it by this row prime, which is in the commutant algebra. And then it turns out that the modular operator leaves the states psi with respect to which it is defined invariant. And then again, if you make use of this identity, then you see that I can replace this row prime with this row here. And then when you look back at this definition here, then you see that I've proven cyclicity of this trace relation here. So traces should have also certain other properties, but this is the basic idea of how you can do it. If you don't follow the details of what I'm showing you here, it's not so important. It's just to give you some intuition why these modular operators are actually important to define something that is actually a trace. And now when you look at this on the left side here, in the trace, I have no psi subscript, but then I define the trace in terms of something that refers to a particular state in the Hilbert space. So it turns out that actually, at least for type 2 algebras, this construction here is unique up to an overall constant factor in the trace. So the trace on type 2 algebras is unique up to a constant state independent factor. And this is something you can see here. Basically, when in this construction here, I can multiply rho by some constant c and rho prime by the inverse, and rho prime also by that constant. Doesn't change this delta psi here, but it would actually change the definition of the trace here because it would reflect in this here. And it turns out that exhausts the different possibilities. So in particular, in general, this is not a Hilbert space trace. It's important to note, though when you do this for trace for type 1 algebra, so like, for instance, finite dimensional ones, you can reproduce the standard Hilbert space trace with it. But now, when you have such a trace, then you can also define density operators that reside in these algebras, these regional algebras that you're interested in basically the usual way. You will just require that for all states in the global Hilbert space and all the observables in the regional algebra, this rho phi, the density operator, basically reproduces all the expectation values. And when you have such a density operator, then you can just and the trace, then you can just compute entanglement entropies for the region in the standard way. So again, this does work for type 3 algebras, but for type 2 algebras, this works. And now, when it comes to von Neumann types, so here's maybe just a brief overview. So they exist broadly 3 types. They have some sub-classification. That's not going to be so important here. These modular operators that I talked about, you can define them for all types. The factorization that I talked about, it doesn't exist in type 3 algebras, but type 1 and type 2. These traces, therefore, also don't, turns out not to exist in type 3 algebras, but they do exist in type 1, type 2. And therefore, because the trace exists, I can also define density operators and the standard von Neumann entropy in these cases here, but not for type 3 algebras. And also, the fact that the modular flow, that there can exist in a modular flow, so generated by elements in the algebra, that is something that you can only have for type 1 and type 2 algebras. And for type 3 algebras, that is not possible as part of basically some of the defining features. And now examples in physics of these different types of von Neumann algebras. So for instance, in quantum mechanics, basically all the algebras that we're usually interested in, particularly the set of all bounded operators on a Hilbert space, they're type 1 algebras. In quantum field theory, regional algebras are typically type 3. And basically the statement is now that regional or gravitational algebras, when you address them in particular ways, are actually of this type 2. And so you can define entropies. Now, let me explain why CLPW in the end introduced what they called an observer. So we're back at the Zitter space here. And generally the expectation or the assumption is that in perturbative quantum gravity, these regional algebras, as already mentioned, that they should be type 3 von Neumann factors, so have no traces and so on. And so when we do this in perturbative gravity, these algebras, they would now contain all the quantum field degrees of freedom, including the gravitons, particularly the Zitter static patches. And now one thing is that, so I mentioned already that CLPW, particularly when you want to go to perturbative quantum gravity, you should impose constraints. And in particular, boost constraints, it's a closed universe. So isometries are also small diffeomorphisms in that case. So you should impose them as constraints, as gauge constraints. And so here in the Zitter space, this boost Hamiltonian turns out to be the modular Hamiltonian of the Bunch-Davis vacuum. So you should impose them as a gauge constraint. I actually have a bit more to say on how you should think of these Hamiltonians from the point of view of perturbation theory later. That wasn't discussed by CLPW, at least hopefully if I get there. And so, and basically you want to look at the gauge invariant algebras, so the algebras that are invariant under this boost Hamiltonian. In fact, you should also look at other diffeomorphisms, but for the moment, we're only going to consider this boost Hamiltonian. And now the crux is, it turns out that this boost Hamiltonian happens to act what is known as ergodically on these regional algebras, which means that the only invariant observables that are contained inside them are trivial, so they're just multiples of the identity. So what that means is there's no interesting regional gauge invariant observable that you can associate with one or the other static patches. So in order to do interesting physics that are somewhat localized to a region, you need to add degrees of freedom. And this is why CLPW added an observer. So as they will turn out to be quantum reference frames, let me maybe briefly explain quantum reference frames and quantum clocks from the point of view of quantum reference frames in a particular setting. Quantum reference frames are, of course, a much wider field. Before I go into this, let me maybe mention very briefly that there's by now a whole potpourri of approaches to quantum reference frame covariance. So there's a bunch of different approaches that you find in the literature. And for the novices, to make things worse, they're inequivalent in the general case. Then one might wonder which one is the right one. It turns out that that's not really the right question to ask, because quantum reference frame covariance can mean different things in different circumstances. So you can't really say that there's a single right approach that fits all possible applications of quantum reference frames. But actually, if we want to talk about gauge theories in gravity, where you do impose constraints, in particular also on states, and it turns out that actually this approach down here is the appropriate one. This is what we call the perspective neutral approach that we have developed in recent years. I should say that also in the context of these cross products and these observers in quantum field theory, there's also been a discussion by the York group and Kassia Reisner, Chris Fuster, and so on, using this approach here. And that is actually also very nice work. And for the algebraic considerations that they made there, this is also perfectly fine to do. If you want to go into these entropy discussions where you also look at really the entropies associated with physical states that do satisfy the constraints as in gravity, then you should go this way here. This is also, at the end of the day, equivalent to what CLPW did. So this is basically an additional step that you do on top of just looking at gauge invariant observables. Okay, so here's a very basic idea of this perspective neutral approach in some sense in a nutshell. You can look at this reference if you want to have some kind of gentle introduction to it. The very basic idea is we start out with some kinematical description of, here in this case, I have two reference frames in some system. And this is basically the Hilbert space on which whatever symmetry group acts on that I'm interested in. And I will consider this as basically a description of all the degrees of freedom of the total composite system relative to some external reference frame if you want. This external reference frame may be fictitious, and in particular in gravity, it will be fictitious. But you can think of this as basically a description relative to an external frame. And then what this perspective neutral framework does is it removes, basically wipes out any of the external reference frame information. It basically takes the symmetry group, it treats it as gauge, and basically averages over that group and wipes out any of that external frame information to give you a completely relational internal description. And in particular, this is what we're going to apply here also to these to the case of this group generated by the boost constraint in the end. And that gives you what is sometimes called a physical Hilbert space. So this is going to be this space here. And we call that sometimes a perspective neutral space. You can think of that as a description of, or that's the set of states that are internally distinguishable, so distinguishable relative to internal reference frames. These internal frames are going to be quantum reference frames. So everything is quantum here. And then you can ask, what does it mean to jump into quantum reference frame perspective? And there are certain maps that I'm maybe going to explain a bit more for the case of clocks later. That turn out to be, you can think of them as sort of quantum coordinate maps that are unitary maps that take this gauge invariant Hilbert space into some gauge fixed descriptions, which you can interpret as the internal descriptions or the internal perspectives relative to different reference frames. And then because these maps turn out to be unitary on these gauge invariant Hilbert spaces, you can basically build something that looks like quantum coordinate transformations, and these are unitary, and in this way you can change quantum reference frame perspective. And now the crux is that here the system, this can be completely general, and in particular it could also be a quantum field theory, and this will be the case in this discussion here. So, and when we now come to this setup of observers in...
Sorry, just a short question. Sorry to interrupt.
Yeah.
So in some of the interesting cases, that group that you would be averaging over is a non-compact group. Is that then technically an issue? It makes things a bit more subtle, or?
Yeah, I mean, it makes things, of course, much more subtle, definitely. So, and indeed, I mean, in the general case, when you have a non-compact group, the construction technique that is used here is basically has to do with the construction of what are sometimes called, I mean, it's usually group averaging in a general sense. Sometimes it goes under the name of refined algebraic quantization or method of co-invariance. There exist different ways of dealing with it. And so this is This is nothing specific to this approach here. This is just something in general about constrained quantization for gauge theories. But it's true that for non-compact groups in general, the convergence of these methods is not known. And also, when you build these Hilbert spaces, the inner products, whether or not they're positive definite or so, there's no general proof that tells you this. But there are many examples that have been studied where this is the case. There are also counterexamples, I should say. But that's not an argument against this approach per se. It is just basically telling you that this point of view of treating these symmetries as gauge, it doesn't work under all circumstances. But that's still fine. And yeah, so that's basically the upshot here. But in the context in which we're going to be working, where it's basically just a translation group, it actually works fine.
Thanks.
Okay, so yeah, so what we're going to be dealing with is a hybrid quantum mechanics, quantum field theory scenario. Why do I call it quantum hybrid? So, so the system we're going to be looking at is, well, the quantum field degrees of freedom in space-time or in these regions. And now what we want to add is basically, because we're interested now in this boost constraint in the Ziller space associated with this given cosmological horizon, we want to introduce clocks to basically deparameterize the flow generated by it. So yeah, so we want to have quantum reference frames for that kind of gauge symmetry. So we want to have suitable quantum clocks. But because we're only looking at a one-dimensional subgroup of the total diffeomorphisms, we only need well, quantum reference frames for a one-dimensional group. And so these are just quantum mechanical reference frames. So in that sense, it's a quantum mechanical quantum field theory hybrid, quantum mechanical frames, quantum field theoretic system. Okay, so and what we're going to be interested in is a constraint where that corresponds to this boost flow, where you have the modular Hamiltonian sitting here, and then we have some clock Hamiltonians here, and the relative sign here just corresponds. It takes account of the fact that the boost has basically a time evolution that goes forward in one patch and backwards in the other. And so this framework falls into the kind of scope of a couple of papers that we wrote a few years ago with Alex Smith and Max Locke. And I'm just going to very briefly get to this here. So we described in there how to build clock states and observables for these cases. And in particular, we're going to focus at the moment for simplicity on Hamiltonians, clock Hamiltonians. So basically, there would be these guys here that have a non-degenerate and continuous spectrum. That's ultimately also what will correspond to what CLPW have done. We'll reproduce that in that way. So it means in particular, they're going to be generators of the translation group. And you can define clock states for any such Hamiltonian this way. You take the eigenstates of the energy eigenstates of this Hamiltonian, and then you basically just build such an integral where you integrate over the spectrum with uniform spectral density. And then you call these basically the orientations of the clock, and well, they take value in the real, so they're kind of group valued. Yeah. And they satisfy this covariance property here by construction, where this is just the exponentiation of the clock Hamiltonian. So basically, it just shifts it uniformly forward. And then you can build covariant POVMs with respect to these clock observables in this particular way. So you kind of integrate them over, say, intervals of the real line, and then that gives you probabilities for the clock reading a value from a certain interval. They're normalized, so you can use them to define probabilities. The important thing is that these clock states are in general going to be fuzzy unless we're dealing with what we call ideal clocks. Ideal clocks, they will become relevant later. They're the case when the spectrum is just a full real line, in which case these are just, the overlaps are just delta functions. Okay, so yeah, and when we have these clocks, then previous construction, was there a question? Sorry.
Yes, excuse me. May I ask whether the spectrum of the Hamiltonian must be bounded below or not? Are you assuming?
So here we take any Hamiltonian that has a non-degenerate and continuous spectrum, The interesting cases will be bounded from below, but it also contains a case when it's unbounded, and that's the ideal clock.
Okay.
So when it's unbounded in both directions, then it's an ideal clock.
Okay.
But in principle, you could have any Hamiltonian, well, that has a non-degenerate continuous spectrum here. In what I'm telling you applies to that case. I mean, you can generalize this also to degenerate ones and discrete spectra, but I'm not going to discuss this here.
Okay. Thank
But
you.
you're right that the physically interesting cases are when it's bounded, and in fact, that is also interesting in this entropy discussion. Maybe you can ask me later if I forget to talk about that. So, but in any case, so we're going to specify this framework for quantum reference frame covariance, this perspective neutral one, to this case of clocks now. So this group averaging is just averaging over this group of the generated by the constraint. And we have now the quantum field theory here as a system. And then you can think of this perspective neutral space as the space of states that solve the constraints in the sense here. And then in this case, these reduction maps into the different clock perspectives, that you can define them as these Page-Wootters reduction maps. If you're familiar with the Page-Wootters formalism, yeah, you can use basically just condition on the clock reading. It turns out they're unitary on the physical Hilbert space, on the gauge-invariant Hilbert space. At first, it might be surprising because it looks like I'm throwing away information by conditioning, but the reason they're unitary is that this is nothing else than a gauge fixing, and I'm gauge fixing something from a gauge invariant description, and I don't lose any gauge invariant information. And that they are unitary is something that we showed in these works a couple of years ago. So, and then this way you can then link different clock perspectives, and at the end of the day, we call this perspective neutral because that Hilbert space essentially contains all the possible quantum reference frame perspectives and links them. Okay. So that's the basic idea here. I should talk about relational observables because they will become relevant. So yeah, one way to compute them is to define them here is again by kind of group averaging, and you can do this in this case here. So we have some system observable. So I guess in our case that will be a quantum field observable. And we condition on the clock reading a certain value tau, and then we just average the whole thing over the gauge group basically, and that gives us a way of having a gauge invariant way of asking, for the value of this observable fs when the clock reads tau. And in particular, when this is an ideal clock, so the spectrum is unbounded, then this simplifies vastly, and it just becomes this just an exponential here, where t is, I realized that I deleted this on the previous slide. Okay, t is just the clock observable that's conjugate to the clock Hamiltonian in that case. When it's an unbounded one, that's the self-adjoint operator. And when I ask for tau equals 0, then it just has this very simple form. And I mentioned this because this will become important in these cross products later. Okay. Now there's another thing that we need in order to understand these cross products, and these are what we call reorientations of the quantum reference frame. To give you a little bit of intuition of what they are, you can think about a tetrad and special relativity. And there are some systems, say some 4 velocity, and reorientation of the tetrad, something that you could model by, for instance, a Lorentz transformation that only acts on the frame index, but not the spacetime index. So it will only act on a tetrad, but not the rest. And so we'll leave all the other tensors invariant. So it could do something like this here. So that changes the relation between the frame and the remaining degrees of freedom here, the system. And so it reorients the frame. And with clocks and a relation dynamics, the counterpart of this is really nothing else than you just look at basically the evolution of the clock without doing anything to the system. So it leaves the other degrees of freedom invariant. And in particular, this is in our case, it commutes, of course, with gauge transformation. So it's a physical transformation. It just changes the relation between the system and the clock. And in particular, when you conjugate these relational observables with these reorientations, it translates this tau label here, as you can see. So that is actually a physical evolution. So it basically takes the observable from measuring the system when the clock reads tau to measuring the same observable when the clock reads tau plus s. Say, it's a gauge invariant one. Okay, now let me come to explaining what this story of observers has got to do with this, and what the messages of this slogan PW equals CLPW. So here's just the slide recalling why an observer is needed. So this is the same thing that I had before. So it's that the regional algebras that are invariant under the modular flow are trivial. So that's why one should add some degrees of freedom to get something non-trivial. And this is why CLPW then added these observers in the antipodal static patches. And in the beginning, they add really what are ideal clocks. So they add basically just momentum Hamiltonians to the Hamiltonian. Why that is consistent, I'm not sure if I'll have enough time to discuss this. We'll see, but you should think of this basically as being sensible in the perturbative quantum gravity regime of G Newton going to 0, so that you can neglect back reaction and so in particular interactions between the clocks and the rest. And now they look at basically an augmented invariant regional algebra under this whole thing. So before we looked at basically the regional Q of T algebra that's invariant under just the modular Hamiltonian. But now this gets augmented to including the algebra of operators associated with a clock. Let's say here this gamma, let's say in that region, and then we look at the invariant subalgebra of this. So basically the part that's invariant under the total thing here, the total constraint. And then the crux is that it gives us a von Neumann algebra that has a non-trivial form, and this is actually what is known as a cross product. And when you stare at this here, then you will see that this is nothing else than the von Neumann algebra generated by the relational observables associated with that ideal clock and the reorientations of that clock. So in that sense, this gives a nice interpretation of these cross products. That so there's some more technical definitions of it, but here from the point of view of quantum reference frames, you can really think of them as always being a von Neumann algebra generated by relational observables and clock reorientations, or more generally, quantum reference frame reorientations, always affiliated with an ideal quantum reference frame. It's important that it's ideal here. Okay. And so this is the reason why I explained you these other things before, so you can understand this here from the point of view of quantum reference frames at the moment. But the reason why they were really interested in this is that the regional quantum fields, degrees of freedom, the algebra, so this one here is a type 3 factor, so has no traces and so on, as I mentioned before. But this cross product here actually happens to be a type 2 factor, and so it possesses traces, density operators, and entropies. Okay. I guess I'm running a bit low on time. How much more time do I have, Natalia?
Let me see with 10 minutes. I don't have my clock. Okay. Let's say 3 minutes, but you had some questions in between, so just go relax it. It's not strict.
Okay. Yeah, I was going to give a bit of intuition for why there's a type conversion, but maybe let me just go quickly through this.
You can go on the intuition. It's a nice part.
Okay, so the reason is basically, so this thing here is by construction gauge invariant. The constraint is this here, and now the crux is basically that if you look at this cross product algebra, and now you look at the modular flow, so the one that is generated by the Q of T Hamiltonian, that's by way of it being gauge invariant, so commuting with this thing here, it is actually equivalent to conjugating the same algebra with the clock reorientations. So why is that important? This is that before this modular Hamiltonian is not actually contained in the regional Q of T algebra. It was an outer automorphism, but these clock reorientations they are contained in the cross product algebra. So that tells us that this flow is actually has become an inner automorphism now. Okay, so the crux of this is that basically the inclusion of the clock reorientation has internalized this modular flow. And as I said before, that a modular flow cannot be inner for type 3 algebras. So this already tells you that this can't be a type 3 algebra. That it is a type 2 algebra, not type 1 or so. This is something that requires a bit of extra work, but this is something that you can show by, for instance, by these trace constructions and so on. But this provides you a bit of an intuition of why this is not a type 3 algebra. Okay, so it's about the clock reorientations that and the addition of them that internalize the flow. Okay, let me maybe move on. So really what this means is that the description here relative to these clock quantum reference frames yields some sense well-defined entanglement entropies, and so in some sense an intrinsic regularization of them. More precisely, it's really these entanglement entropies, what is really well-defined entropy differences, and that has to do with the traces being unique only up to a scaling with a state-independent constant. Okay, so now what is the slogan PW equals CLPW? So if you look at that paper, CLPW then provided a description of physical states and observables where you impose constraints, and the crux is that it turns out to be equivalent to the Page-Wootters reduction of this perspective-neutral framework as we showed in these works. So in that paper, you find a map that is given in this form here that they take as a description of what they call these co-invariants of these physical states. And in particular, so here, this is the original kinematic Hilbert space. And then it gives you a map to the U of T Hilbert space and then the first clock. And it is defined in this form here. And so here, actually, the way I'm spelling it out here is generalized to non-ideal clocks. In that paper, it's given in terms of what would be called ideal clocks. And then if you stare a little bit at this equation, then you will see actually that this is nothing else than basically imposing a group averaging, this coherent group averaging, and then doing a Page-Wootters conditioning on the clock 2, so the clock of the complement reading 0. So by Page-Wootters conditioning, I mean, really, it's just you basically throw the bra tau 2 equals 0 on this physical state. So this is then really just a Page-Wootters reduction, or basically jumping into the perspective of this observer in the complement, into the perspective of the complementary observer. And then when you look at also how they describe their regional algebras in terms of this map, it turns also out to be equivalent to the Page-Wootters reduction of gauge-invariant algebras that we described a couple of years ago in this paper. And so that basically tells you that the description that they use and the formalism that they use for describing what they call co-invariants of physical states and observables, the representation on these physical states is equivalent to the Page-Wootters formalism. And so that leads to this slogan PW equals CLPW. CLPW then go on. So because it's type 2, there's a trace density operators, and so some entropies exist. And at least for product states, they then, so at least when they start out with an ideal clock, they take product states and then they, with a sufficiently peaked clock state, they then show how to compute approximately density operators. So it's using approximations. And then they also show that it actually reproduces the form of the generalized entropy, as I mentioned. So,
Philip, can I interrupt you a second? Sorry. Hi. So just to point out that being type 2 doesn't necessarily mean that entropies exist, right? Because it has to be type 2 1 or type 2n, because if it's type 2 infinity, they don't, right?
What do you mean they don't? I mean, you still have density operators that you can compute in that case, right? So then
no, but if you have type 2 infinity, right, the traces don't exist for like everyone.
No, that's right. Yeah, that's true.
So I really liked your argument why it's not type 3. Yeah. But then you still have to show that
that's right.
All traces exist. So I mean,
Yeah, no, I mean, you're of course right. That's not all for type 2 infinity. And okay,
and
actually
one
coming back to,
infinity too. Yeah. Mhm.
yeah, I mean, coming back to actually one of the previous questions about bounded Hamiltonians,
Mm.
I guess you know that anyway, but when we have these ideal clocks here, so unbounded Hamiltonians, it turns out that the cross product, well, the cross product algebra is actually always type 2 infinity.
Right.
So the type 2 1 algebras you only get when you get actually Hamiltonians that are bounded
But
below, not
below,
above.
yeah. Mhm.
Yeah.
They need some extra.
So it's true that in the case of type 2 1, so when you have bounded Hamiltonians, they're actually subalgebras of the cross product. And
Yeah.
they're actually subalgebras for which every operator is trace class. But for type 2 infinity, you're right, not every operator is trace class. But you know, there still exist states for which you can compute the entropies.
For sure, yeah, but it's not like obvious. Okay, no, thank you. Just wanted to clarify this. Thank you.
Okay, so here CLPW computes. They start out by computing basically the reduced density operators for ideal clocks at first, and then later they project it to the case when you have bounded clocks. But really, the whole construction here is of their density operators, and the entropies is actually an approximate one, and it's only true for these specific states. And so actually what we did is we completely generalized this, and I'm not sure if I will get to this. So I guess I have now -3 minutes. Can I still go on a bit, or maybe I'm going to skip this part here. So here, this slide is basically about a justification of why one should be looking at cross products from the point of view of perturbation theory in gravity. Maybe I should skip this. I'm not sure how much time I have. So
I would be interested to hear it.
Okay, so just go on.
I would suggest that you use a few more minutes, because usually we have discussion and you had several questions. We started 5 minutes later.
Okay. So because I mean, this slide is in some sense tangential. It's important to understand why cross products, but kind of the main thing about our generalization of the cross product construction and so on, that comes afterwards. So, but anyway, maybe
audience, we have a clear wish of the audience to see this. So just go on.
Yeah. Okay. So one can ask now, of course, when we think about perturbative gravity, so the G Newton going to zero limit, why one should be looking at these types of constraints, these boost Hamiltonians. And one thing that I didn't explain to you, and that's also not explained by CLPW, is that these cross-product generating constraints, these boost Hamiltonians are actually of second order in the expansion parameter kappa. And so, in particular, what that means is they're quadratic in the graviton field H. I mean, that's intuitively clear because Hamiltonians should be quadratic, at least in the kinetic part. But you can actually prove this, that because we're dealing with isometries, that diffuse constraints in closed universes with associated with isometries, the first order part is exactly zero. So it's identically zero. There's nothing non-trivial in there. And so one can ask, why should I be imposing second order constraints when I'm interested in the G Newton going to zero limit, where I'm mostly interested in the linearized theory, so the first order. And one can also ask, why is it sufficient to look at a single constraint, or maybe a finite number of constraints, where we're dealing with a field theory that has infinitely many constraints? And the answer to that question has to do with what are known as linearization instabilities in symmetric backgrounds on compact Cauchy slices. So this is a subject that goes back to the 70s and 80s. Has been a little bit forgotten, but it's actually quite important. It holds actually for any theory with local gauge symmetries, but in particular for gravity. And the statement is essentially, if you perturb around a background solution, where the background solution has symmetries, such as killing symmetries in our case, then there will exist perturbative solutions at linear order that are inextendable to higher orders, or they are inconsistent with exact solutions. So what that means is, if you take the solution space of your theory, so in our case GR, exact solution space, then you can think about really perturbative solutions at linear order as really being sort of tangent vectors, or being vectors that should be tangential to the exact space of solutions. And now the point is, when you have symmetric backgrounds, there will exist linearized solutions that you can think of as vectors that are not actually tangential, like this red vector to the solution space. And so, and these are spurious solutions that have nothing to do with the full theory. And basically, these are the kinds of solutions that you want to avoid, right? So you don't want to make wrong predictions that are inconsistent with your full theory. And now it turns out that, and that's kind of a remarkable result, that in order to avoid these, so these are called linearization instabilities, that you have solutions that are not actually, that are spurious. And the remarkable result is that, at least in gravity, on compact Cauchy slices, that a solution is stable, or it is extendable to a higher order if and only if what are called top charges, if all the top charges vanish. And what are the top charges? They're the gauge constraints with all the independent killing fields in your theory. So in particular, in our case, the boost Hamiltonian will be one of those top charges. And when you impose all of these linearized, all of these top charges, then the linearized solution is actually consistent. And now you can ask, well, there's more killing fields in the de Sitter space, but it turns out that the other killing isometry, or the other isometries in the de Sitter space, at least, they don't actually affect this type transition. And yeah, so this wording wasn't used by these in this previous literature, but that's really how you can think of it. And so then, so basically, this gives you an essentially unambiguous justification for spatially compact spacetimes with boost symmetry, why you should impose these higher order constraints. Or so basically, you impose all the linearized constraints, and then you impose all the second order, all the top charges, which are of second order. But then, for our purposes, to talk about this type transition, all but the boost Hamiltonians are actually uninteresting. So that's why it's actually sufficient to look at just the boost Hamiltonian. But what that implies is also that you should think of all these algebras that I've discussed, and also the kinematic Hilbert space that I mentioned. You should think of those as actually already obeying all of the linearized constraints of the theory. Okay, so basically the assumption must be that the regional algebras already obey all the linearized constraints of the theory, as do the kinematical states. Okay, and so then on top of it, we basically impose this top charge. But basically, in this sense, you can think of the cross product as being a necessary byproduct of ensuring that the linearized solution is consistent. All of these arguments here are actually classic, I should say, but there exist some strong arguments that in quantum theory this should also be true. Okay, and okay, maybe I'm going to skip this here, but okay. Yeah, maybe let me also, yeah, okay, maybe one statement is that when you have black hole spacetimes, you can also consider cross products. In those cases, you don't have, they're not compact Cauchy slices. The same argument doesn't actually apply. Neither does it for these general subregions that are discussed by Jensen, Soros, and Speranza. That's not an argument that you shouldn't consider cross products, but it is making clear that you should look for a better justification for why you should look at cross products in that case. There's no necessity in terms of the consistency of the theory to look at those in the G Newton going to zero limit. Okay, but in the de Sitter case, you have to. Okay, now let me get to the final part. Okay, I guess I'm horribly over time, but this in some sense maybe the main message of the talk, that these regional algebras, these regional entropies are actually observer dependent or quantum reference frame dependent. Again, if you want to have a sort of short overview, there's this the summary paper. And this has something to do with what we call relativity of subsystems. That's something more general in quantum reference frames. Doesn't only hold in this context. And it's basically a statement that if you have a general gauge invariant algebra, and you have several quantum reference frames in the game, and you have some system, so in our case, the quantum field theory, and you want to look at the relational observables describing that the system relative to these frames. It turns out that these algebras, well, describing the system relative to the first frame and the second frame, they define distinct subalgebras of the total gauge invariant algebra. Okay, so that means really what one frame basically calls the quantum field in our context will correspond to different degrees of freedom from the gauge invariant point of view than what another frame calls the quantum field degrees of freedom. So really, in that sense, yeah, frames R1 and R2, they mean really different gauge invariant degrees of freedom when they refer to the subsystem S. So that's kind of important. So in general, these can overlap in some non-trivial way. The overlap will really just contain all the degrees of freedom of the system that are already gauge invariant themselves, so which you can think of as internal relational observables. And now this has implications, of course, for correlations, entropies, thermodynamic properties, and blah, blah, blah. All of this will become quantum reference frame dependent. There's a systematic investigation on this paper. Basically, what we're going to do is just a more sophisticated application of this. And we want to apply the subsystem relativity to this context of observers in gravity. So far, we had only one observer per causal region. And the system is basically their respective regional Q of T algebra. But in subsystem relativity, really you need to have basically several observers or several quantum reference frame to see the same system. So that means we actually have to add observers to the same region. So that means we should populate spacetime with more observers, and that's what we did. You can just throw in as many observers as you want. So basically, we expand the kinematic Hilbert space with as many observers as you like. So in our case, we're just going to look at, again, just a bunch of clocks, and they can be non-ideal and whatever. And so we expand the total constraint in this way. This also makes sense from this perturbative analysis, but I'm not going to go into this. And then you can look at more general, these invariant algebras that you can look at that I had before, but now you can include more clocks, any subset you like, and you look at the gauge invariant part of it. Turns out there will also always be type 2 algebras. You can classify all these different type infinity, type 1 cases. In fact, as soon as there's 2 clocks involved, it will always be type 2 infinity for those, for the experts. And then now what we want to do is basically we want to build all these traces and density operators as before, and then compute entropies. And now there's a very non-trivial aspect in this whole construction, which is that the Hilbert space here will now typically not contain any tracial states, any cyclic separating states that I described before. So we can't actually use in any way the trace construction of previously used in the literature, so we had to invent something new. And this is a little bit more technical, and since I'm out of time, I'm just going to go very coarsely over this. If you don't understand the details of this, it's not so important, but it's actually technically the main output of the paper. And the consequences of this are maybe more interesting, but basically, what we do is we take note of the fact that for type 2 algebras, as I mentioned, the trace is unique up to scaling. So that means you can use any auxiliary Hilbert space on which this algebra has a representation and that contains a tracial state. To define a trace. That's what we do. And so basically that's essentially using a Q of T vacuum and a thermal field double state for the clocks that does the job. Now, then you have to basically map it back to the Hilbert space that we're interested in. This is something that can be done by relative modular theory. And then we have to explain what we mean by the trace that we so construct in terms of the physical representation on the physical Hilbert space. Turns out that in most cases, this representation is actually faithful. You can show that. That's the case if and only if there's a complementary clock exists. And in any case, then basically in line with what we had before, you can construct density operators for physical states, global physical states that solve the constraints in some sense, the obvious way. And then, as I already mentioned, using relative modular theory, that's mostly for the experts, you can get an exact result for arbitrary physical states that I'm not going to explain in detail, but this is basically the form of it. So you have, for the experts, some relative modular, relative Tweeter operators in there. So the crux is here really, so CLPW and all the previous constructions, they only worked for very specific global states. For instance, also CLPW's construction was only approximate. This here is an exact result, and it holds for arbitrary physical states, arbitrary global states, and also arbitrarily many observers. And you can show also that this construction actually recovers the examples in the previous literature, but it's really a significant generalization. And you can also show that for also a generalized notion of semi-classicality, you can reproduce the generalized entropy. And you can also show that you get actually corrections for states when you have entanglement involved. Okay. So this is a bit technical, that part. So it's a bit hard to explain in detail in a talk, but that's basically the bulk of our work. Now coming back to the subsystem relativity, so this bites also here in this case. So when I have, for instance, two clocks or two observers in a region, and then what they refer to as the Q of t degrees of freedom, the overlap of the corresponding algebras will actually turn out to be trivial in De Sitter space, and that has to do with this ergodicity that I mentioned before, that the pure regional degrees of gauge invariant algebra is trivial. And so really that means that one clock and another, what they refer to as the Q of t algebras, they overlap as trivially as it gets, really. Okay. And so it shouldn't be surprising that then for the same global state, the entropies that you can associate with these different algebras that will correspond to the entropies that the different observers will associate with the Q of t degrees of freedom, the subregion, that they may wildly differ actually. Now, proving this in detail, and it turned out to be somewhat complicated, but we gave actually a number of cases where this happens. And so we show also explicitly where this happens. And one example is, for instance, where you use something like a gravitational interferometer. But maybe I'm not going to say more about it because I guess I'm already way over time. And basically, that's the upshot. So here's the rough summary of it. So the observers in these perturbative quantum gravity constructions are just quantum reference frames. Basically, the presence of these relational descriptions, they give you, in some sense, an intrinsically regularized description of these entropies. And we have the subsystem relativity also for gravitational algebras, and it implies this entropy relativity. Okay, and then there's one thing that I just mentioned in a single slide is that you can understand these gravitational algebras as basically being the necessity of considering them in the form in which they appear in these cross products, really by these linearization instabilities. Okay, and I think I'm just going to leave that here now. So thanks very much for your attention.
Oh, thank you very much, Philipp. And do we have more questions of the participants? So go ahead, Kasia.
Yeah, so I want to go back to your argument for Y cross products, which is something that I always wondered about for gravity. So one thing which I don't understand is that, so your full symmetry is diffeomorphisms, right?
Yeah.
Yes. So, I mean, in principle, I should be looking at invariance under the action of the diffeomorphism group.
Yeah.
And then somehow, but well, the bit that's generated by these first order and second order constraints, that's much smaller than the whole diffeomorphism group. So you kind of, I kind of understand what you do or what we do in De Sitter, because the group is much smaller and you quotient by part of it and the rest kind of remains there. But how do you think of it for diffeomorphisms? Because it's really large.
No, that is really the argument. Okay, maybe I went a little, maybe I didn't explain it as well, but this is really, this is about diffeomorphisms here, because
all of them?
Yeah.
All of them.
So that's really it. So basically the statement is you look at all of the diffeomorphisms at linear order.
Yes.
And only the isometry only the isometry diffeos at second order.
But what about the other orders? I mean, why can you ignore?
Well, okay, I mean, we're in perturbative gravity, so we don't care about the other orders.
Oh, okay, fine. Yeah. But
the statement is that if you only looked at the linearized order, so if you only look at the algebras that are invariant under all the infinitely many linearized diffeomorphisms, and you look at the solutions of that, you will find solutions that are inconsistent with a full series.
Yeah, okay, that I understand. So do you have an idea how to generalize it to all orders, or to like any finite order you want?
Well, the statement is really that. That's why this G Newton going to 0 is important. The statement is that in order to have perturbative consistency, it is just sufficient to look at this, what I mentioned. So to look at all the first order constraints and only these finitely many second order constraints. That's sufficient.
Yeah.
So in order to have perturbative consistency, you don't need to look at, you have a good approximation to an exact solution if you do this.
Yeah.
So,
that makes sense.
Yeah. But of course, that doesn't stop you from getting more and more accurate approximations by going to high orders. Of course, that you could in principle do. But it turns out that these instabilities they don't arise anymore at higher orders. So basically, as soon as you kill off the linearization instabilities, there are no higher order instabilities that arise. So it turns out that once you close all of these second order top charges, that guarantees you as long as
classically, that makes total sense. Okay, so I mean the crucial thing is that you are really looking at the perturbative regime for small g, and that
Yeah. But for instance, indeed, I mean, if you're familiar with this work by Janssen, Sohr, Speranza, where they look at general subregions, for instance, this argument here doesn't apply in that case because so basically, I still think it's a very interesting paper, but in that case, there's the justification for why you should be looking at the at these second order constraints that generate the cross products is to me open. So they give an argument in that paper which I don't think is quite right. So this argument based on linearization stabilities is for me pretty unambiguous. But that's not to say that you shouldn't look at products also in the other cases. But it's more it's explaining that you have to have some other reason for why you want to look at it, and in particular need to be interested in higher order observables, such as, for instance, in some cases, second order observables, and they turn out to be important, for instance, for including area fluctuations and so on. So they appear in these constructions or considerations of the generalized second law, for instance, in this context of cross products and so on. There they turn out to be important. So if you're interested in those, okay, then you look at these higher order constraints. But from the point of view of perturbative consistency, there's probably no reason to do so. And that's a point that, in my opinion, is completely neglected in all of these previous works, in particular also in the context of black hole spacetimes, where there are no instabilities.
Yeah, no, that's I really like that argument. Thank you for a very nice talk. I'm afraid I have to go and give a lecture, but I will watch the rest of the discussion later. Thank you, Philipp.
Cool. Yeah, thanks very much. Bye-bye.
So Albert, I think you want to make a question.
Yes. So again, as I mentioned before, a very nice talk. I think you managed to give a very nice intuition about the complex topic, even to those who are not, so much into it. So you had to skip at the end. So I think you had there an example involving a gravitational interferometer. So could you maybe, use maybe now the time of discussions to elaborate a bit on that point you had at the end?
Yeah, sure. So okay.
This one, yes.
So people familiar with quantum reference frames might understand why I'm looking at this. This has to do with which is ultimately a consequence of subsystem relativity, but it's basically that quantum reference frame transformations they can map product states into entangled states and superpositions. Conversely into something that's entanglement. And this is basically something that we're applying here. So basically this gravitational interferometer, so the setup that we're using is basically which I'm not describing here. We have 3 clocks. So we have 2 in one region. And from the point of view of one clock, basically, in one quantum reference frame perspective, we're sending the clock 2, for instance, through a gravitational interferometer. So you can think of that as, okay, there's some massive object or so, and you have a clock state, or I guess pointer here at the bottom, and then you basically send it into superpositions of clock states. And then we can map into basically the perspective of that clock afterwards. And this is basically an example where the superposition. So this is going to be our clock 2 is going to be our new quantum reference frame. And when in an old perspective, the new quantum reference frame is in a superposition of orientations, and the clock readings are its orientations. Then in the new perspective, when I go to the perspective of clock 2, then I will get an entanglement of the old quantum reference frame. In that case, I guess clock 3, I suppose in this case, with the rest of the degrees of freedom. So, and that's
also,
of course,
just to make sure that would also kind of correspond then to say that in that description you have a superposition then of the massive object at sort of different locations generating the.
Well, okay. In principle, in principle, yes. So if you look at these kind of cartoonish pictures that I guess the Vienna group sometimes presents, you could think of it this way, but here you should think of this massive object in some sense. It's a bit external here, okay? So it's not actually explicitly modeled in the quantum degrees of freedom here. Well, although you could in some sense think of it as being part of the QFT degrees of freedom. So, and indeed the entanglement that will be generated between what is then the third clock that is not pictured here will be with all these other degrees of freedom, including QFT degrees of freedom afterwards. And so then that means, so if you start out with something where there's a product state, then afterwards you get something that's entanglement state. So that's already suggestive that there is going to be a change in entropy. Now, to actually prove this and to make that in some sense rigorous turns out to be much more complicated. So there's a lot of details that I'm glossing over. But because in particular, in our case, it turns out to be good to deal with non-ideal clocks, in which case they become fuzzy and so on. And then you need to be a bit more, it involves a bit more formalism, but this is basically the kind of the intuition behind what is happening in our case. And then, so basically this entropy relativity that we then see explicitly, this is something, that has to do with, basically this entanglement relativity that I'm mentioning here. Okay. So that's really a kind of rough summary of that.
Philip, I would like to take opportunity on this question, something related that it's a very basic question. Because when you're talking about clocks, there was one sentence in some slides that you were telling, measure something when observer measures tau. And I would like to understand, what is this observer in this situation? Is the observer, like when you change your quantum reference frame and you have this clock where you're going to measure tau?
Are you talking about this here? Or?
Yes. How can I understand who is measuring, who is reading tau, and who is measuring what?
Yeah, okay. And that's a valid question. And maybe I'm a little bit careless in the wording that I'm using here because I'm not actually talking about measurements really in this whole setup. But you could think of it, so a proper discussion of measurements, is a bit separate. But you can still think of it as what I mean by, well, no, actually, maybe it is fine to say that it measures Fs when the clock reads tau, because so when you think of this whole thing, it's really an operator that in a gauge invariant way. So if you were to measure this observable, it would basically measure, the property Fs conditional on the clock being in state tau, right? So, but of course, then you would have to measure this observable. Then the question is, who measures that observable? So this is where, in the gravitational context, the meaning of this is maybe a priori not entirely clear, because because what it would mean is, so we're looking at states that satisfy the constraints, all the constraints. So we would think of those as being basically, all the degrees of freedom in the universe in some sense. Now, if I do a measurement and I have a collapse of the state, somehow that's, collapse of the wave function of the universe, and roughly speaking. So what is the meaning of that? Okay, that's a separate question. So this gets into, conceptual, foggy regions that I wanted to keep out of. But it is something that is valid to state when you can do this in laboratory experiments. There are some experimental realizations, for instance, of the Page-Wootters formalism by a group in Italy, for instance. There you could think of measurements that are being done on the evolving system in this relational setting, that they correspond to these relational observables, but then it's basically the external observer in the lab that's measuring these observables on the system that's kind of simulating these relational dynamics. Okay. So, but yeah, in this gravitational setting, I think you're basically, you're touching on, I guess, a vulnerable point in quantum gravity more generally. That's, But,
so but in the formalism, without thinking about applications, just in the math, you are thinking about the observer who would be measuring this is someone outside using the quantum reference frame as your frame.
Okay, yeah, I mean, actually, okay, maybe so maybe from the point of view that CLPW probably also have on this is that one could ask, why do they model an observer with a clock? Well, so the important thing is that the clock is, has dynamic degrees of freedom that are needed to basically augment this algebra from something non-trivial to something, from something trivial to something non-trivial. But really, they think, of course, of the observer as being some world line in the background space-time. It's a perturbative construction, so we have some background space-time. There's an observer traveling in it. For example, like a Lorentz observer in Minkowski space, and they just happen to be equipped with this clock. But the observer itself, the agent is somehow not modeled by these degrees of freedom. You can think of this clock as being a device that they carry along their world line, and somehow the device happens to be included in this description, whereas the agent himself is not. And then, yeah, you could, I guess, if you take that point of view, then you could say, well, yeah, if that these observables here, they define in a gauge invariant way what that observer would measure, measuring that the observer measuring the system property Fs when their clock reads tau. Okay. So I mean, yeah. By the way, I should say that, and unfortunately, I will have to go in like the latest 5 minutes because I have to pick up my daughters from daycare.
We have to finish here anyway. It's already giving the time
that are closing. But maybe here, I mean, if you just look at this thing inside here in the bracket again, you have this operator Fs, and then you're conditioning on the clock reading. So if you just look at this thing, that makes it in some sense clear that you're measuring Fs conditional on the clock being the clock state being in reading tau, and basically the averaging around it is nothing else than making this thing gauge invariant. Okay, because I'm averaging over the gauge group. That's all I'm doing, really.
Okay. Thank you very much, and thank you very much for the seminar. If there is someone who would like to add something just for 1 minute, we just raise your hand. So, okay, so we will stop the recording. I think there is no